Got it. Okay. Is it recording now?
Yeah, seems like it.
Okay. Okay, let's get started. After a very long gap, we are again back to the Let's Learn session. So this is the session number 28, and I'll be discussing on image captioning, mostly related to the reinforcement learning techniques, whichever I have applied to this to improvise the results. Why is this? Okay. So initially, I'll start off with some basic terminology and the introduction of reinforcement learning, and later discuss how reinforcement learning can be applied to sequence-to-sequence generation tasks. And there are some concepts known as scheduled sampling and word gate model. All those things I'll discuss later and show the results that I have obtained with the different approaches. Okay, so coming to the use case image captioning, this is the architecture that I worked upon, which I had shown recently. This particular architecture uses image features as well as text features. So the image features are obtained using the ResNext pre-trained model. So this ResNext model is basically pre-trained on 3.5 billion Instagram images. And this dense caption model, basically what it does is given an image as an input, it will detect the bounding boxes of objects present in that particular image. So at the bottom, we can see a sample of it. In this image, there are a lot of objects that this dense cap model is able to detect. And in each bounding box of the object it has detected, it will label a particular caption of what it has observed in that particular bounding box. So here you can see a lot of descriptions or captions for each of these individual boxes. So these two are the pre-trained models that I have used. Basically, there would be around 50 to 100 descriptions or captions that will be generated by this dense cap model, but I'm randomly choosing only 5 of them during the training phase of this model. So once these two features of image and text are extracted, those are sent to the respective image encoder as well as the text encoder. And later on, they are passed on to the decoder individually. So once these are passed on to the individual decoders, we are merging the outputs of individual decoders of whatever the model has been extracted for both image as well as text. And later, the merged output of both of these decoders are sent to the linear layer, which will map whatever it has learned to the vocabulary space. Here, the vocabulary size is 10,453. So it will give the probabilities of the word outputs for all those words in the vocabulary for the next word. So apart from whatever is mentioned above, the one more addition was the personality traits that I had discussed before. So whatever the 216 personality traits are there, we want our model to generate the captions according to those emotions or the personality traits. I'm just concatenating the personality traits as well to the word embeddings. So here the word embeddings size is 1024. That means for every token we'll be having 1024 dimensional vector. And in order to concatenate the personality traits as well, I need to maintain the same dimension. So I'm generating the embeddings for each of these personality traits with the same dimension 1024 as the word embedding, and later concatenating both of these as a multi-style component. So once you concatenate, the dimension of this particular thing will be 2048. So these word embeddings are sent to the decoders while the decoding part. And so since the personality trait is also embedded, it will generate the captions according to those personality traits. Coming to the dataset description, this is a YFCC 100M dataset, which was having around 2 lakh images. And these are the individual splits of the image in training, validation, and testing sets. Coming to personality traits, there were 2 and 6. And coming to captions, there was one reference caption per image in training and validation sets. And for test set, there were 5 reference captions per image. And this is the one of the image with respect to personality trait and captions from the training set, just to get an idea of how the data set looks like. Okay, so coming to the basic terminology of reinforcement learning. So just to get an idea of how this works, I'll give an example. So suppose you would be aware of playing chess with a computer operated opponent, right? So basically how the opponent learns is based on whatever the steps or actions we take at each and every state in the chess game. It tries to learn from the actions we choose in a particular state and try to figure out whether we are able to win or lose from a particular action that we have chosen. So that's how the remote control, the opponent would be able to learn. So initially it might fail because it is still learning from the actions we take. But as and when it plays a lot of games, it will be able to learn which is the best move in a particular state. So that's how reinforcement learning basically works out. This can also be related to a newborn baby. So a newborn baby, how it learns to walk, or whatever it learns in the early stages, so it obviously does mistakes. It will fall down. So based on the actions it takes with the experiences, with the negative experiences, we are assigning a negative penalty, and with positive experiences, we give a positive reward. So that the newborn baby will be able to appreciate what it is doing correct and what it is doing wrong, and it tries to learn from those experiences and tries not to repeat those mistakes. So this is something similar to that.
I think this was a special example for Kirtana, right?
Yeah. Yes. And this is another example is suppose this mice is stuck in a maze. So how does it try to come out of the maze? So what actions it has to choose at a particular instant of this maze so that it can easily find out the way out to the maze. So initially it will try to explore the kind of steps it needs to take at each and every instant. And if it is not able to reach the exit of the maze, it will give itself a negative reward and tries to improvise upon itself by further exploring the environment. And as and when it reaches the goal state, that is the exit of the maze, it will reward itself with a very high positive score. So here the goal is usually to maximize the reward. So reward is anyways dependent on the actions the agent takes. So here agent is the mice. So whatever the actions it takes, it is given a reward with, and the goal is to maximize the reward. So that is the basic fund of reinforcement learning. And one more thing is policy. So policy is something kind of a blueprint which tells you if you are in a particular state, which action you need to choose in order to maximize the total reward. So this policy is what basically is unknown. So reinforcement learning, you don't have any data as you have in supervised learning or unsupervised learning. There you at least have the inputs and outputs. In unsupervised learning, you just have the inputs. Here in reinforcement learning, you have nothing. So you just have to generate the data and learn by experiencing that kind of a data. And based on the reward structure and the policy, this particular policy gets learned during this reinforcement learning process. So coming to the neural networks, maybe I'll talk in the next slide. So introduction to reinforcement learning in sequence generation. So Here, the recurrent models that we use for sequence generation can be viewed as the agent. So the agent can be similar to what here the mice is doing. So here the agent is the LSTM model. And the LSTM model, we are giving the image and word features as the input. So you can regard the environment, which was the maze in the previous slide, to the words and image features. The parameters of the network can be the policy. So policy, since I mentioned, it maps which action you need to take in a particular state. So that is the LSTM parameters itself, the weights, activations, all those things, which we are supposed to learn. So that's what it means, the policy. And action is, so here the action was maybe left, right, down. So these kind of actions it has to take in order to reach the exit of the maze. So coming to sequence generation, the actions would be the words in the vocabulary, because that's what you are supposed to predict at each and every time step, right? So you have maybe suppose 5,000 is your vocabulary size, and given that you have already generated 2 words in your sequence, so the third word will be dependent on the first 2 words, and the third word is chosen from the vocabulary of those 5,000 words. So that is the action this agent, which is the LSTM model, will take at each and every time step based on the words and image features that you have given as the input. So after each action the LSTM model takes, that is after it chooses each and every word in a particular sequence in the time step, it updates its internal state, that is the cell state and the hidden states of the LSTM layers. Upon generating the end of sequence token, the agent observes a reward. So this is what, like, suppose you have completed generating a particular sequence, and the end of sequence token is triggered at after it generates the complete sequence. So the LSTM model observes a reward. So here reward is something like the metrics that we choose to evaluate the model. So like blue score, ROUGE, CIDEr, all these are the metrics that we use to evaluate a model. So we just use these kind of metrics as the reward function. So as and when these scores or the reward is higher, we tend to say that the model has converged and model is able to generalize properly. So since that is the goal that we are supposed to maximize. And the goal of training is to minimize the negative expected reward. So since we deal all the neural network approaches, the objective function we try to use as a minima. We just use a negative value and attach it to the loss function, so that it is a gradient descent instead of a gradient ascent. And as I mentioned, we use the CIDEr, blue score, or ROUGE scores as the reward functions. Any questions till now?
No questions. I like that you're
Okay.
comparing it with the mice example. That really helps.
Yeah. Okay. And the RL-based techniques. So there are value-based approaches and policy-based approaches. So I'll just discuss about the policy-based approaches. So this policy gradient, this reinforces an algorithm which tries to update the LSTM model parameters along with the reward that it has observed for each and every token it has generated. So what this does is, this is the same loss function that you have seen here. So this is the expected total expected reward for the complete sequence. So this loss function, so here multiplying the rewards with log probabilities. So like this p theta of WS is the probability for the entire vocabulary that you generate at each and every time step. And you are taking a log softmax of those probabilities for a computational efficiency, and you are multiplying those probabilities with the reward it has obtained for each and every word it has generated in a particular token. So you're supposed to minimize this as much as possible, since this is a negative over here. So basically what this tries to do is, for a particular word in a particular time step, if that is a good word, then you would get a higher reward over here. So you're multiplying a higher reward with the log probabilities. So basically, the model would have given an output of a distribution of the probabilities for the entire vocabulary. For those specific words which are having a higher reward, will when you multiply with those log probabilities, the log probabilities will increase a bit more for the only specific words which have higher reward. For words which are having lower reward, it will get suppressed. So you're basically trying to initially these log probabilities at the initial stage of training phase, it would be something like a uniform kind of a distribution, where many of the words would be having higher probabilities. So as and when the model learns, you are trying to transform this kind of a uniform kind of probability distribution into something similar to a normal distribution, where only specific words will be having higher probabilities, and irrelevant words are given are assigned very less probabilities. So that's what we are trying to achieve over here. So that's what this loss function does. So reinforce with baseline, what this does is, since here the vocabulary spaces are higher, like 5,000, 10,000, 20,000. So it will be difficult for reinforcement learning based techniques to choose a particular action in so much big vocabulary space at each and every time instant. So it takes infinite time to learn such a large action space for reinforcement learning based techniques. So the variance with this kind of a loss function would be definitely higher, because this is a stochastic reward function, and each and every time step it is choosing some word initially, and obviously it is trying to change a lot of things over the probability distribution, even if it is not necessary. So in order to reduce this kind of a variance, we try to subtract this reward function with a arbitrary baseline function. So this will significantly reduce the gradient updates that we are doing in this loss function for these log probabilities, and tries to address some of the issues of getting stuck in local minima, those kind of problems that we usually face during training. So this is the next approach. So these are the methods how this reinforcement algorithm has evolved. So initially it was just the reinforce. Later, with the addition of the baseline, it is a reinforce with a baseline. This self-critical sequence training is the next update of the reinforce with a baseline. So here in the baseline function here, this was an arbitrary function or a baseline function. So this had nothing to do with the reward function over here. So in self-critical sequence training, what the modification we do is the formula still remains the same. But here the baseline function is here, instead of it being a independent function compared to the reward, we are making it dependent based on the sample reward. So how this works out is, here you can see, so this is basically the LSTM layers, which is trying to generate each and every word in a particular sequence. So here you can see there are maybe 2 or 3 layers in this LSTM, and based on the hidden states and cell states, it is generating words sequentially over here. So once it is generating all the words, at the end of sequence token, we would be generating the complete sequence. And with respect to the ground truth tokens we compare the blue score or CIDEr score, and we'll get a particular value for the CIDEr score. So if the CIDEr score is higher, we say that it is in sync with whatever the ground truths we are expecting, and the score would be higher. If it is less, we try to improve it during the training phase. So here there are 2 sequences over here. So so in this formula, RWS is the reward that we get by sampling each and every word during the training process. And the bottom one is the baseline function. So we try to put this training, the model that we are training in every particular epoch, we try to put that into an evaluation mode, that the mode that we use in inference. And we try to get the tokens in the particular sequence by using the argmax function. So basically in at inference stage, when we use a beam search or a greedy search, so usually we use greedy search, but since the beam search gives better sequences than greedy search, we try to use beam search. But when you use greedy search at each and every time step, we are trying to find the token which is having the maximum probability, and we try to choose that particular word in the sequence. So in for this baseline function, what we do is we put the model that we are training into an inference mode and try to sample the tokens for the complete sequence and calculate the CIDEr score. And we treat that as a baseline function and subtract this from the originally sampled model during the training phase. So here, this formula still remains the same, and this B is replaced by the argmax greedy decoding search that we do. So as I mentioned before, this higher reward than baseline reward will be pushed up or increased in probability, while samples which result in lower reward will be suppressed. So what happens is during whatever the CIDEr score we get during sampling, during the training phase, and when we are subtracting with the greedy decoding, when this particular function is negative, what it means is the sampled words are horrible than the greedily decoded word. So we try to decrease the probability of those sampled words in this log probability distribution. And for those, when this complete function is positive, that means the sampled word is better than the greedily decoded word. And we try to increase the probability of those particular words and decrease the other irrelevant words. So that's what we are trying to satisfy this loss function by doing the updates with respect to self-critical sequence training. Any doubts over here?
Yeah, I have one question. If you would use it without the bottom sequence, would you end up with the same result, but then it just takes longer?
So yeah, so without the bottom function means it will be this formula. So since right now, if the vocabulary is too small, maybe suppose maybe like 50 words or 100 words, then this might perform better. But when you have a very large action space of the vocabulary, 10,000 words and all, even though you use this loss function, you'll really not able to converge properly. I'll show the results of this later.
Okay.
Okay, and coming to the reference paper that I used, initially I tried out with just this self-critical sequence training approach, but the results were far more worse. So here, basically, what happens is it is not like during training phase, I straight away use this reinforcement learning as a loss function from epoch 1. It doesn't work like that. So I try to train this particular model with supervised learning techniques itself for maybe 5 epochs or 10 epochs, and later save that particular model and use that model to train further using these kind of reinforcement learning techniques. So whatever the metrics that you have achieved using supervised learning, the main goal using reinforcement learning is to further improvise it. So when I did the same thing with this SCST algorithm, whatever the metrics I had achieved till supervised learning, the metrics got even worse than whatever I have achieved till supervised learning because of a high action space. Later, I found out one more paper which tried to discuss the disadvantage of using the SCST approach as it is. And they tried to improvise it by adding this kind of a word gate and adaptiveness to this SCST algorithm. So the thing that I was able to implement was based on, so this was the architecture that they showed. And I was able to implement this word gate to this architecture that I had showed previously. So what this word gate does is, here maybe it's better to discuss from here. So here you can see this LSTM, it is decoding each and every word sequentially. So one more addition to this particular usual architecture is I'm sending the image to a fully connected layer and later to a sigmoid layer and calculating the loss with respect to it. So basically on a high level, what this does is when you give an image, it is not like the LSTM is supposed to decode the higher vocabulary space. Like an image can be represented by maybe just 5 or 6 kind of objects that is there in the particular image. So there is no need of using all the words in the vocabulary to generate the caption for a particular image. So there are the objects that are detectable in a particular image is very limited. So you are trying to learn only those particular set of words in the vocabulary which this image represents actually. So that's what this this additional layer is trying to do. So sigmoid activation function, since you are sending it over here, so it will give the since the sigmoid value varies from 0 to 1, you will get all the values for the words in the vocabulary ranging from 0 to 1. And those specific words which actually help in describing a particular image, the value will be higher. And all other irrelevant words will be having a very less value. So that's what it learns over here in this additional layer. So after it learns this particular thing in this additional layer, I'm trying to multiply this with the probabilities, log probabilities that we get at each and every time step. So when you do this, what happens is whatever the log probabilities we'll get for all those 10,000 words in the vocabulary, when we'll get multiplied with this word gate outputs. So whichever the words that will actually represent the image will amplify the probabilities, and all other irrelevant words, it will suppress the probabilities. So in that way, the model will be able to actually choose only the actions which are relevant, and all other irrelevant actions are discarded. So that's the advantage of this word gate model. It is reducing the action space. And apart from that, so this loss function, as you saw in the previous slide, here the one more modification is in order to reduce the variance of this reward function, we are trying to additionally introduce these two parameters and dividing with a ratio. So what this does is this is basically the average of the sample reward and the average of the greedy reward. So this function is basically normalizing this complete subtracted value. So this will significantly reduce the variance and whatever the issues this plain SCST model was suffering from. And coming to this one more concept, that is scheduled sampling. So sequence to sequence models, they suffer from exposure bias. So basically like a translation, summarization, even autocomplete, all these are sequence to sequence models, even this image captioning. So here we basically during training, we give the decoder the ground truth tokens at each and every time step in order to calculate the loss function. So how in this image, suppose at the time step 1, the model has predicted something. We try to calculate the loss for this particular time step by using this predicted or generated token with respect to the ground truth token we have. That's how the loss is computed. So, but the disadvantage of this approach is during training, we are showing all the ground truth tokens to the model, but in inference, we are not showing that. So because of this, whatever the model has learned during the training, it tries to use the same kind of words during the inference as well. So there won't be any kind of diversity as such, because for image captioning, when you say during training phase, as I mentioned before, each and every image is fed with just one ground truth token, right? Just one ground truth caption. But every image can be represented with infinite number of captions, right? Like you can write in a infinite number of ways for a particular image how a caption can look like. So when the model has to get more diversity in how it has to generate the captions for unseen images during inference, it has to be more diverse. So in order to increase the diversity of the model during inference, we try to use this scheduled sampling technique. So here, this technique gradually replaces the ground truth tokens with the model's own predictions during training. So here, instead of showing the ground truth tokens to calculate the loss function for the generated caption at time step 1, we try to use the generated caption itself. So whatever the generated word here in time step 1, we try to use the same thing to calculate the loss over here. So this is not done 100% during the starting phase of the training itself. This is gradually increased. So this is something like a coin flip that they have here it is shown. So maybe like 50% of the times we try to use the ground truth token to calculate the loss, and 50% of the times we try to use the predicted or generated caption or token to calculate the loss. So this will increase the diversity in captions that are generated at inference, and the model will be able to generalize as well for unseen images. And coming to the model hyperparameters, so these are some of the hyperparameters I have chosen with a distributed data parallel training. So here I have used 5 epochs with a supervised learning. So after the model has reached a particular stage where it knows something with supervised learning, later I used reinforcement learning for 3 more epochs to further improvise the whatever the metrics it has learned during supervised learning approach. So here the loss functions, initially for supervised learning, it is cross entropy. And for the word gate model that I showed, so this particular extra layer, I'm using the binary cross entropy. And reinforce with baseline is the loss function for reinforcement learning. And the training time, it was 1 hour per epoch for supervised learning and 1.5 hours per epoch for reinforcement learning. And these are the evaluation metrics, blue score, rogue score, and CIDEr score. So these are n-gram based formulas which try to tell how close the generated caption is with respect to the predicted caption. And CIDEr score is much more better than these n-gram based techniques because it relies on TF-IDF frequency as well as cosine similarity along with the n-gram based overlap. Coming to the results, plain baseline model that I had showed the architecture in the initial slide without any kind of reinforcement learning or word gate model. So the plain baseline model was able to achieve these kind of metrics. So this was in sync with what it was claimed in the paper. And later, I introduced this word gate model. Okay, basically before word gate model, just by using the baseline with the plain SCST approach. So since I mentioned because of the large vocabulary space, the metrics got declined when compared to the baseline model. So whatever I had achieved before got worse when I introduced SCST approach to further train the model. Later, when I introduced the word gate to this particular baseline model, you can see the metrics are slightly improved. And when I combined the word gate with Adaptive-SCST approach, you can see there was around 10 to 15% of improvement in the evaluation metrics for all these blue score, rogue, and CIDEr scores. And these are some of the captions that were generated for different personality traits for these images. You can maybe just go through some of these. And coming to the conclusion, I guess I basically sums up whatever I have told till now. Yeah, that's it. Any questions?
So,
Nice.
Yeah, great actually. So because we are using that reinforcement learning, we don't have to like think about training it to specific data set, is it?
Specific data
Like
set means?
do we do like because it's taking 10 hours to train, what about do we have to like fine tune it for customers? Then that time that how the time that it's taking, isn't that too much?
Yeah, this is more only because the data is also more, right? 2 lakh images are there, so definitely it will take a lot of time.
So like fine tuning would be faster.
Fine tuning, No. Yeah, fine tuning will be faster. It depends on how much data we have. Yeah, definitely.
Okay. Nice.
And one more thing to mention was previously I had tried implementing the research papers a lot of times, but never I was able to replicate the exact results whatever they had claimed, because most of the times it happens that they would have not revealed each and everything that they have done during the model training. Some hyperparameters might be missing. So obviously each and every parameter will be necessary to replicate whatever the results they have claimed. But this time I was able to reach that phase of whatever the paper mentions. I was able to get those numbers, and apart from that, I was able to improvise it with these kind of reinforcement learning based techniques. So this word gate model actually, when I just used this plain SCST approach, when the numbers got decreased, I was very angry, because that's what not supposed to be using these reinforcement learning approaches. But later when I found out the disadvantages and tried to implement these word gate models, this loss function and all, the numbers improved. I was finally satisfied with what my understanding was. And this particular addition to this architecture, I was able to do very quickly, maybe within 1 or 2 days, which even I didn't expect I will be able to do. Yeah.
Great work.
Stephen, any questions from your side?
No, no questions.
Okay. Then I guess we're stop.